in our development here of the idea of vectors, it's time to look at forces, because we've already analyzed forces, Newton's laws. And since force is a vector, let's see what the implications of considering its vector nature is. So the accelerating force is the net force, and it's a vector quantity. So we must take into account the direction as well as the magnitude of the forces that are acting on a particular object. And we should be thinking in terms of free body force diagrams, because that is the approach that leads to the correct solution about what's happening to a given object. Well, two forces acting 50 newtons east and 140 newtons 30 degrees north of west. Let's determine the net force. We're going to do that using two methods. First of all, graphical. So we get our geometry instrument and we construct a scale. A scale that'll work in this case is probably 1 centimeter is 10 newtons. As you can see, for 50 newtons then we'd have 5 centimeters. So that should fit on your paper comfortably. After we do this, we'll then do the trigonometric method to see how that works as well. So we have a reference line, and we're going to start right there. First of all, putting the 50 Newton east vector on there. So we measured this out to be 5 centimeters. And then 30 degrees north of west, we bring in our protractor. So west is this way, 30 degrees north is that way. So right there is the location that the vector passes through, and it's 4 centimeters. So there's the two forces, fully specified. And now let us add the vectors. So they're both acting at this point, but to add them we go tail to tip. That's how we do it all the time. Adding vectors is tail to tip. So there it is. The resultant will be this. So we measure the resultant and measure the angle, and it's 2.5 centimeters at an angle of 52 degrees. So the net force is written as sum of F is 25 newtons at 52 degrees north of east. Fully specified. Now, let's pretend that this force is acting on a mass, 5 kilograms in particular, and this is the net force, so let's figure out the acceleration. So the acceleration is a vector, and it looks like this. The sum of the force vectors over the mass. Mass is a scalar, so 25 newtons at 52 degrees north of east. We fully specify the force and divide it by the scalar mass, 5 kilograms. Now, the scalar affects the magnitude of the resulting physical quantity, which is acceleration. But does it affect the angle? And I'm sure you realize the answer is no, it doesn't. So the answer is 5 meters per second squared, 52 degrees north of east. And we've solved our vector and force problem. We are now ready to solve it trigonometrically, but before we do so, let us make some observations about how we handle components corresponding to a given vector. So here is our vector A, 4 centimeters at an angle of 35 degrees from the horizontal. We're going to resolve that A into east and north components. Now, before I just plunge forward, take a look at this vector and ask yourself, does any of this vector act southward based on this reference frame? Act downward, south? You say, no, none of it acts south. Well, how about north, upward? And you say, yes, it does go upward. Does any of this vector act west, this way? And you'd probably honestly answer no, but you would confess that indeed it does act east. So there's a east part and a north part. And those this vector can be uniquely resolved into those two components and effectively replace it, or the addition of those two components would be the same thing as the original vector. So, how do we do this? You don't have to do this every time, but I'm going to show it real explicitly here by drawing a reference line to the tail of the vector, and just like this. So I'm doing a horizontal reference line in this case. And then I'm going to draw one perpendicular through the tip of the vector. So there it is. And since one's horizontal and one's vertical, they are perpendicular to each other, and that's a right triangle. So we have a right triangle here. Now, the vector is drawn from the tail of A to the intersection of the two reference lines. Right along here, there's the intersection. And that's how much east the original vector is. That's how much eastness it has. It possesses eastness. Now draw a second vector, actually a component, from the intersection to the tip of A. Just like that. And there it is. And we can measure how much the eastern component is. And we get 3.3 centimeters east. The northern part, the north vector, 2.2 centimeters north. So there they are. Okay, so the steps for resolving trigonometrically is simply repeat steps 1 through 4, but you don't have to do it to scale. You can just do it freehand. Then use right angle trig, calculate the components. So the eastern component, well, with respect to the hypotenuse and the angle, the side adjacent there is a cosine of theta. So what is that? Well, it's 4 cosine of 35, which is 3.28. Hey, that's very nicely close to our graphically constructed answer. And the north, a sine of theta. And a sine of theta is 4 sine of 35, which is hopefully about 2.2. Yep, it was very close. So that's how you do it. Now let's go back and do that original problem that we did with the two forces and see how that works out. Okay, let's bring back the problem we had before with the two forces, 50 newtons east, 40 newtons 30 degrees north of west. And let's use trig. With our expanded designations here for our reference frame, north, south, east, west, and also plus or minus y, plus or minus x. So both are totally valid. You can kind of take your pick. So reference line, we'll start here, put in the 50 Newton force east, and also the 40 Newton force 30 degrees north of west. Again, these can just be freehand just to get a visual perspective on the progress of your problem solving. That's actually pretty important because you may forget something. So got everything labeled there. Now we need to get the components. So we have the x components and the y components. A in the x direction, how much xness is this? And you'd say, well, all of it. Yes, 50 newtons. Well, what's a in the y? A in the y, nothing. There is no y component. Let's do the same thing with vector b. For b, we got our x component and our y component. B in the x direction, well, just the hypotenuse times cosine of 30. So 40 cosine of 30. by 40 sine of 30. Now, once we have those components identified, I'd like to wiggle out the hypotenuse so that we don't try and add it again second time. So just kind of clears that out, realizing you don't have to think about this anymore, and all the components are what you see here. So speaking of which, the resultant will be the x and y components that have been summed. In other words, the resultant is the resultant of the x and the resultant of the y as components, as vectors, I should say. Those two components, x and y, as vectors. So the total amount in the x is from both the a and the b, and that's the sum of the forces in the x. 50 minus 40 cosine of 30, which is 15.4. And the resultant in the y, sum of fy, 0 plus 40 sine of 30 is, so there's our components of the resultant. So now we can kind of quickly freehand sketch the resultant. It has Rx, of course it also has Ry, and those are perpendicular to each other, and then we have the resultant with an angle. So this is our right triangle that we reduced all this down to. Now the magnitude of the resultant, Pythagorean theorem. So that magnitude, square root of the sum of the squares, is 25.2 newtons. Easy to do on your calculator. What about the angle? Well, the tangent of the angle, tangent of theta, is opposite over adjacent, Ry over Rx. So let's get the angle, which is the inverse tangent of Ry over Rx. There it is. Calculator gives us 52.4 degrees. So putting together the magnitude and the direction into our expression for the answer, we have 25.2 newtons at 52.4 degrees north of east. So we could either say north of east or 52.4 degrees with respect to the positive x. So the positive x, and we swing by definition, by convention, we swing counterclockwise for the positive angle. And there is the problem solved using trig. So the method we just developed and demonstrated for graphical or trig, dealing with components, can be applied to any number of components. And usually you have the option, but a lot of times the graphical method, even though you may not think it's quite as accurate and may not be or precise, it nevertheless produces an adequate answer to meet the purposes at hand. So, but you need to be familiar with both methods. So just make sure you can do either. Now, we want to finish this thing by discussing briefly forces in equilibrium. And it just simply means that all the forces acting on the body don't produce an acceleration. So then it's in equilibrium. Well, let's use an example of this puck, and there's 3 forces acting on it. 2 will be specifically shown here, F1 and F2, and F3 is not shown. So the solution to find the third force is knowing that all the forces add up to 0. So we add the 2 known forces together to get the resultant. We bring in the 6 and 1. The assumption is that I've already measured this, and now I'm right now parallel moving it over here. So here it is, parallel moved, and then drawing the resultant. Now we of course can measure that. And the sum of the forces is 0. So the third force, which is called the equilibrant, has to uniquely cancel that resultant of the first 2. So bring in the instrument again, measure the resultant, and simply construct a vector in the opposite direction of the same length. There it is. And now we have F3, that is the third force. So that's kind of nifty. Let us consider a sign. This is typically where an equilibrium problem comes in, is analyzing a sign. We have a sign here that's held by 2 wires, typically called guy wires. So there's tension in those wires, and we're going to figure out what the tensions are. Not using numbers, but again, relative vector sizes. So we can draw the weight in, and it acts straight down. We don't know how big it is, but, well, yes we do. It's this big, whatever that vector length corresponds to. So this is just a conceptual example. Now, there's kind of a list of rules to solve this thought process. You know what the equilibrium is, so we can draw it in. What I mean by that is these 2 wires pull in such a way as to resist gravity. So the equilibrant to this FG is just an equal vector in the opposite direction. So we can draw that in. And we know that the 2 components, the component of tension here and here, add up to give us this equilibrant. So the way we're going to find what those are is to construct parallel lines through the tip of the equilibrant. we draw a parallel line through here, parallel to this line, and parallel to this line through the tip of the equilibrium. So there it is. There's the other one. And now the forces actually act along the wires, and we know that the magnitude of those forces is simply where the intersection of the line is. So there is force to the right and force on the left. Those are the correct values of the vector forces for this problem, given that the weight is equal to this. So that's a pretty useful problem-solving method that would be a little more difficult in general to do it strictly mathematically. And in this case, you didn't even have any math. I didn't show any numbers here, so really the only way to do this is to do it graphically. So that's why you need, one more reason why, you need to know the graphical method. So in the next video, we'll do a couple of examples of just Newton's law problems using vectors.